The question now is the resistivity of the material a constant value or it depends on the temperature? Actually, the resistivity of any material depends on the temperature. And most materials, their resistivity increases by increasing the temperature. So if we are talking about the variation with temperature, the relation between temperature and resistivity for copper or for metals in general is nearly linear over broad temperature range such that the new resistivity minus the standard resistivity at specific temperature T naught equals the standard resistivity rho naught multiplied by temperature coefficient alpha multiplied by the difference between the new temperature minus the standard temperature T naught. So assuming that we have the resistivity of copper at temperature say 30 degrees and it is required to find out the temperature at 50 degrees. So 50 minus 30 multiplied by alpha multiplied by the resistivity at 30 degrees, we will find the difference between the resistivity at 50 degrees minus 30 degrees. Okay? Here temperature is selected as a reference temperature and rho naught is a resistivity as this temperature. Temperature here can be represented into absolute value or it can be represented in general degrees. So we can say that T naught is 293 Kelvin at room temperature and rho naught, for example, at the room temperature for the copper is 1.69 multiplied by 10 to the power minus 8. Because the temperature enters only as a difference, it doesn't matter whether you use centigrade or Kelvin. So we can use centigrade degrees or we use Kelvin degrees, but we must use one scale. So either in centigrade or in Kelvin. So it doesn't matter whether we use centigrade or Kelvin scale in that equation because the size of degrees on both scales are identical. Alpha is called the temperature coefficient of the resistivity. This shows that the equation gives good agreement with experimental temperature in the chosen range. So generally speaking, here is the resistivity as a function of temperature, and we can note that the resistivity is increasing with increasing the temperature. The slope of this curve is effectively the temperature coefficient of the resistivity. As an example, if you have a rectangular block of iron which has dimensions 1.2 centimeters multiplied by 1.2 centimeters multiplied by 15 centimeters. So this is a cross section area 1.2 multiplied by 1.2 and this is the length. The potential difference is to be applied to the block between parallel sides and such way that those sides are equipotential surface. So we have two streams in the parallel sides. What is the resistance of the block? If the two parallel sides are the square ends 1.2, 1.2. So assuming that the two parallel sides or the cross section area is 1.2, 1.2. The other one is what is the resistance if the rectangular sides are 1.2 by 15. So in this case, this is the cross section area and this is the length. Okay, so we have two different situations and we will see what is the resistance of this one and what is the resistance of this one. In general, the resistance of any sample R equals the resistivity multiplied by the length over the area. So for the case 1, the area is 1.2 square centimeter. So it is 1.44 multiplied by 10 to the power minus 4. Centimeter is 1 to the power minus 2. So by the square 1, 10 to the power minus 4. And the length would be the 15 centimeter. So the The resistance here are, assuming that the resistance or the resistivity of the iron is 9.68 multiplied by 10 to the power minus 8. So rho multiplied by L over A. So the resistance here would be 100 micro ohm. Now, if we assume that the cross section which we are applying the potential is 1.2 centimeters multiplied by 15 centimeters, so this is a new area, and the length in this case would be 1.2 centimeters. So in this case, the resistance rho multiplied by L over A, rho is a 9.68 multiplied by 10 to the power minus 8. The length in this case is 1.2 centimeter, 1.2 multiplied by 10 to the power minus 2. And the area here is 1.2 centimeters multiplied by 15 centimeters, which is 1.8 multiplied by 10 to the power minus 3 meters squared. By calculating the resistance here, we can obtain the resistance is 0.65 micro ohm. It can be quite noted that by applying the potential in two different ways, we could obtain different values for the resistance for the same sample. So the resistance depends on the length across the potential and the cross section area across the current. Okay.